Alchemical Free Energy Simulator, one of the advanced builders in MolCube-Apps, provides a complete setup for alchemical free energy calculations. It helps users build simulation systems, prepare input files, and generate post-processing scripts necessary for accurate binding free energy predictions. There are two main modes available in AFES. The Absolute Ligand Binder allows users to compute the absolute binding free energy of a single ligand, while the Relative Ligand Binder focuses on calculating the relative binding free energies between a set of ligands. In this video, we'll demonstrate how to use AFES to compute the binding free energy between a protein and ligands. To begin, several pre-build projects must be completed. First is the PDB Reader project, where you upload a reference protein-ligand complex structure. This complex will serve as the template for building additional systems. Next is the solution or membrane builder, which generates the environment around your complex. It's important to use the same force field as the one selected during the PDB Reader step to ensure compatibility. Finally, in the Ligand Reader and Modeler project, the ligands you want to analyze are aligned to the reference ligand using the option Use a PDB Reader project. This aligns each ligand to the reference based on the maximum common substructure. Once all pre-build projects are complete, you can move on to the AFES module from the builder list. After entering a project title, you'll select the simulation engine, either Amber, Gromax, or Blade, as well as the type of calculation, such as relative or absolute binding free energy. Then, choose the force field used in the previous step and load the solution or membrane project to define your base system. In the next step, select the reference ligand from the PDB Reader or Ligand Modeler project. You'll then load the Ligand Reader and Modeler project where your ligands were aligned to this reference. From the list of available ligands, move those you wish to use into the selected ligands list. After that, click Generate Morph Set to create morph pairs based on molecular similarity. You can manually modify these morph pairs by adding or removing them. AFES provides visual tools to support this process. The clustering result shows how morph pairs form closed cycles, and you can view 2D structures of each ligand. The similarity score matrix shows pairwise similarity scores, helping you to curate the best set of morphs. In Step 3, you'll review and adjust core atoms for each morph pair. These are the shared atoms used to align the start and end ligands. They are initially selected automatically and shown in red. You can remove or re-add core atoms, but you cannot designate entirely new ones beyond the initial suggestions. Once core atom selections are complete, proceed to define simulation options such as box dimensions, ion concentration, and temperature. When you're ready, click Submit to finalize the setup. In the final step, AFES generates and allows you to download the complete simulation input files. These files are ready to be submitted for molecular dynamics simulations that compute the desired free energy values.